Hello everyone, welcome to another video. Today we are going to talk about ACID properties, which are foundation of reliable databases. So let's get into it. So what are the ACID properties? These are acronyms for four properties. A is for atomicity, and C for consistency, I for isolation, and D for durability. So what are those four properties? Let's get into it. First, we will talk about atomicity, which is all or nothing. So what is the problem this atomicity is trying to solve? For example, say I have to make a money transfer from bank account A to bank account B. So let's say I have account A and I want to transfer $50 to account B. And if we maintain tables for these accounts and their balances, what do we need to do? We need to first deduct the balance of account A by $50, and then we need to add $50 to the balance of account B. So you can see there are actually two database operations that need to happen, and the atomicity ensures that either both of these operations happen or none of these operations happen. So without this atomicity guarantee, what problem can arise? Say I can deduct the balance from account A by $50, but the B account never gets the $50 if that fails, if the second one fails. So we need to do both 1 and 2. Just doing 1 and not caring about 2 is not enough. If that happens, then the $50 from account A is lost forever and account B never gets that money, and that can raise to disputes. So the atomicity is all or nothing. A transaction indivisible unit of work, and either all operations succeed or none do, no partial updates. If any part fails, the entire transaction is rolled back to the original state. So in this case, both of the account transfer operations, both of the operations here are part of a transaction. Next, let's talk about maintaining validity and preventing interference. So there comes consistency. So what is consistency? The database tables and their records can only transition from one valid state to another valid state. What do I mean by that? For example, account balance cannot be negative. So going by the previous example, let's say I want to transfer again $50 from account A to account B. In that case, if I have less than $50 in account A, let's say $30, I can't do that because the account balance would be negative. So always the database has to be in a valid state, and that is what is meant by consistency. And what is isolation? So concurrent transactions are independent. So it might be a bit difficult to understand. So let's say I am doing two transactions, A to B I am doing $50, and A to C I am doing $20. So what will happen in this case? Let's say I start with $60 balance with A. So the first transaction can go through, but the second transaction cannot go through. If they happen at the same time, either the first one will succeed or the second one will succeed, but both of them cannot succeed. But if the transactions are not happening in isolation, what can happen in that case? A to B and A to C, two transfers are happening, and we start with $60, and we have already started with the transaction from A to B, so that should deduct $50 from B. But let's say the state of A has not been updated yet, so state of A still shows $60. So when I do the transaction A to C, which transfers $20, A to C transaction will think that account A has enough balance and go ahead with the transaction. And with isolation, that is something that cannot happen. That means whenever there are concurrent transactions, it should appear as one transaction happens after the other. So in this case, A to B, or either A to B or A to C will happen first. Let's assume A to B happen first. So this will be minus $50 for A, and this will become $10. And then when we try to bring $20 from A, this transaction will fail. And durability, once committed, forever saved. So durability is a basic property of databases. So once a transaction is committed, its changes are permanent and it cannot be reverted back by automatically. And these transactions, when they are saved, they survive the system failures, for example power outages, crashes, reboots, etc. And these are achieved by first writing data to non-volatile storage and then actually committing a transaction, so that even if the system crashes and the system reboots, it can understand from the log that okay, this transaction has happened and I need to resume from there. So it often involves write ahead logging, the example I talked about, and the changes are logged before being applied to the main data files, enabling recovery. So where is ACID applied in practice? So of course you can see that atomicity, consistency, isolation and durability together, these properties guarantee reliability, integrity and predictable behavior in your database. So when should we use it? For example, in financial transactions, banking, e-commerce orders, etc. And then critical business logic, where a lot of changes are interdependent and if one of them fails, everything has to be rolled back. In those cases, the ACID is very important. And then any scenario where data accuracy and consistency are paramount. And trade-offs, achieving full ACID, especially isolation, can introduce performance overhead. For example, as we said, because there is a transaction A and then transaction B, if we don't let them execute parallelly, there can be performance overhead. So a lot of modern systems, they don't require ACID because they don't require data consistency per se, and for them we can go with eventual consistency, and in that case we don't have to rely on transactions and we can make a lot of operations parallelly. In case the data accuracy not very important. So we'll talk about it one video later, but for now that's it for today. Thanks for watching. If you like my video, please like, share and subscribe, and see you in the next one.